So good afternoon, everyone. Welcome to this special edition of the NITEX Colloquium. Today is International Day of Mathematics, and I see all the mathematicians have a T-shirt with a big pie, and they didn't share it with the physicists, so I'm very offended. Yeah. And so it's not only the International Day of Mathematics, it's also the International Year of Quantum Science and Technology. So we are really very happy to have a speaker, Professor Bob Coecke, who covers both bases. Yeah? And Bob, as probably all of you know, is the chief scientist of Quantinuum, one of the leading quantum computing companies. He's also a visiting research chair at the Perimeter Institute and a professor emeritus at Wolfson College in Oxford, where he was previously the professor of quantum foundations, logic, and structures. And there were not many of that kind before him. Yeah? And he's famous because he's one of the pioneers of categorical quantum mechanics. And here were the guys here that do quantum computing know all about ZX calculus by now. Yeah, and some of them also know about DiscoCat for natural language processing and so on and so forth. Some of you might have read one of his two famous books, one on picturing quantum processes with the big dodo in front. Yeah. And those of you that feel very young might have read Quantum in Pictures, which was intended for high school kids. Yeah? So, Bob, we are really very happy that you took the time on a Friday afternoon to be with us, and we are very much looking forward to your presentation. Thank you very much.
Thank you so much for having me. I mean, there's a lot of people I know who are present in the room who can't directly talk to because there's always been a strong connection, especially along category theory with Cape Town and Stellenbosch. So let me just now share my slides. Share. So this is the one I'm going to use. Share. And view. Oh, there you are. View. Enter full screen. Okay, good. So there we are. So I mean, as I kind of announced in the abstract, there's sort of two parts to the talk. The big chunk will be quantum picturalism. I'm saying a new language for quantum. What I mean by that, I will start to explain now. So I'm an emeritus from Oxford University. I still teach there. I still supervise there. So I'm still quite active there. I'm actually teaching in the mathematics department at the moment. My main job is at Quantinuum, and I also have like a visiting chair at the Perimeter Institute. Right, so let's start. And I'm going to start with what I actually mean by the language of quantum. And this goes back to John von Neumann, of course. So John von Neumann, I mean, usually when I give this talk in an audience, I let people guess things. And sometimes, if it's a difficult question, then they get a book for free or something. Now, online, this is a little bit difficult to do. Anyway, this is John von Neumann. So people, of course, know John von Neumann from the theory of games and also like the architecture of the ordinary computer. Sorry, not a quantum computer. But then another important thing about John von Neumann is that he's the father of the Hilbert space formalism of quantum mechanics, which is the usual language of quantum mechanics. Anybody in maths and physics usually knows that. But what people don't always know is that while he published his book on the mathematical Grundlagen der Quantenmechanik in 1932, in 1935, he wrote to his colleague, Birkhoff, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So John von Neumann basically denounced his own quantum mechanical formalism in terms of Hilbert spaces and linear algebra and all these things. Sometimes it's a misconception by people that they think like quantum mechanics is Hilbert space. It's not Hilbert space. It's something built on top of Hilbert space. And von Neumann had to come up with new concepts for that purpose, like density matrices. The projection postulate is also due to von Neumann. So these are all extra ingredients which you put on top, just saying quantum mechanics is Hilbert space, which is quite kind of a naive statement. Anyway, von Neumann himself rejected that formalism in 1935. As some among you may know, he actually came up with a lot of other things, mathematical structures, like with Birkhoff, he actually did something called quantum logic, which was based on lots of non-distributive lattices, and which then also started the study of these things, very fundamental mathematical study of these things. Although as a field of physics, it's kind of vanished. Like, I mean, you still see this quantum logic mostly in like areas like psychology and things like that, where the non-distributivity actually makes sense as a sort of modeling structure. And also, of course, von Neumann algebras were partly pushed by his desire to come up with a new formalism of quantum mechanics. Okay, so the message to remember here is like von Neumann didn't like Hilbert space himself. There's a lot of stuff written about that. Okay, so this is Erwin Schrödinger. So Erwin Schrödinger, of course, is known for his cat and for Schrödinger equation. Something again that people probably know less is that in a paper, also 1935, which is the same year as von Neumann basically denounced his own quantum mechanical formalism, he said when two systems enter into temporary physical interaction, I would not call that one, but the characteristic trait of quantum mechanics. So what von Neumann is saying here, which goes against pretty much everything people have been saying for the past almost 100 years, is that the core of quantum mechanics, the crux, the thing which makes it what it is not really quantum measurement. It's not observation, the fact that observation changes a system and all these things, but it's actually what happens if you bring two systems together. And mathematically, this of course means that you describe them by the tensor product rather than say a Cartesian product or a direct sum, which effectively is the same in category theory languages. But it's really the use of tensor product which he coined as the most important aspect of quantum mechanics. This went completely unnoticed. This went completely unnoticed because von Neumann had a strong emphasis on measurement. He came up with the postulate which basically says if you observe a system, then it changes. And this was something that made people very unhappy, and so philosophers, lots of philosophy books have been written about this measurement phenomena, but nobody took much notice of this idea that composition could actually be the key to understanding quantum mechanics. So I say the key to understanding quantum mechanics, because many people thought that measurement is the key to understanding quantum mechanics. In all the rest of today, we will say composition is the key to understanding quantum mechanics, and that's what pretty much this talk is about. Okay, so this is the Schrödinger story. He thinks that composition of system is the core to quantum mechanics, to understanding quantum mechanics. This is Roger Penrose here at Oxford. So I'm still based at Oxford, where I've been living for now 25 years almost. So Roger Penrose is in maths at Oxford. People know, of course, Roger for black holes. He got a Nobel Prize for that. And then also his father actually was a good friend of Escher. And so they exchanged many ideas, like through Penrose's mathematics, like the Penrose staircase here is then also, for example, the subject of a painting by Escher. So there was a lot of interaction between Penrose and Escher. Another thing which people, for good reasons, know less about with regard to Penrose is that when he was an undergraduate student and had to learn general relativity, he really didn't like the symbols. So the typical symbols you see them here on the left-hand side of the twiggly arrow. So you got these symbols with subscripts and superscripts, and then you have to compose them, do contractions. And it's quite hard to read these things if the expressions become big. So Penrose then felt that if he represented the big symbol by a blob or a box or whatever, and then the subscript and the superscripts by wires, which you can interpret as incoming and outgoing wires. For this talk as a convention, we'll read from bottom to top. So on the picture on the top left, F and G are incoming, and A, B, and C are outgoing. And you can think of the blob as like doing something to whatever comes in to something that goes out, just like in flowcharts, basically, just like in flowcharts. Well, then you can get an alternative notation for what basically this usually tensor notation does for you. Now Penrose did this in his undergraduate in a sketchbook. The first time this actually appeared in a paper was a paper I called something about negative dimensional tensors in 1970, I think, by Penrose in an appendix. And it's only like in the 1990s that two category theoreticians, Joel and Street, showed that formally these pictures are actually a mathematical entity. They're a mathematical entity which are not just an illustration, but an equivalent representation of the tensors. And the way you actually symbolically want to read these wires and these boxes is in terms of something called symmetric monoidal categories. And I know for a fact that there are some serious specialists in the audience today listening who probably are much bigger specialists in the field than me. Anyway, so that's what Penrose brought to the picture. He brought pictures. So okay, anyway, so here you see the connection, which I already explained in words. So okay, let's summarize. Von Neumann wanted a new quantum formalism. Schrödinger said quantum is about composing stuff. Penrose uses pictures instead of symbols, and actually the two latter ones turn out one and the same thing. If you want to have a formalism which is fully based on composing things, in the sense Schrödinger was imagining, and if you want to use pictures instead of symbol, you actually end up in the same place. And so that's what a lot of my work has been about. I have to be honest, like when I started to do this, I wasn't neither aware about like Schrödinger's desire for composition, nor was I aware even of Penrose's pictures. But of course, very soon people pointed both of them out to me. So here's what's categorical quantum mechanics. But I mean, I'm going to focus on this latest picture, which, I mean, people may think that it was written for children, and that's kind of how we've been selling it. But as a matter of fact, it's really for everyone. And it's the whole point about this book, Quantum in Picture, which traces back to a field which Samson Abramsky and I started, which is called categorical quantum mechanics in 2004, which initially was to re-axiomatize quantum mechanics in terms of monoidal categories, which in the line of what I was just been saying is a axiomatized categorical quantum mechanics in terms of composition of system, making composition of system like your first-class citizen of the theory, and which then in terms will be the same as doing a quantum mechanical formalism entirely diagrammatically. So basically, this is the book we wrote. I mean, there's a book before which I'll point at later, but well, I mean, I think, do I have a copy lying here? No, I don't have a copy lying here. But what I do have here, if you can see the camera, is a Lego Dodo. So this is a Lego Dodo, and people refer to this book as the Dodo book because the Dodo in front. It's called Picture in Quantum Processes. It's published by Cambridge University Press. And this is a course, a quantum computing, quantum theory course we have been giving at Oxford University since 2013. So this really is the textbook of that course. Later, I've got a slide about that, and it's sort of known as the Dodo book. It's about 9,000 and the 2,000 pages. What we do in this book is we start presenting quantum theory as part of a more general class of theories using diagrams, but then we also derive the Hilbert space formalism of quantum mechanics, and then we introduce all the usual notions, then like density matrix and all that, as derived from the diagram. So if you're interested in that, you go to this book, Picture in Quantum Processes. Now, I wrote this book, and then we wrote this book. Why did we wrote the second book? Well, it's on the back. Hello there, I want to learn some quantum. Maybe you think you don't know enough maths. Well, that's not a problem. The pictures in this book are a new kind of math that will teach you all about the quantum world. So essentially, we pretty much cover all the same stuff as we covered in the Oxford University, which essentially was a postgraduate course, or third year and fourth year were included some years too. But we do this without any mathematical prerequisites. That was the whole point of this book, to make something that basically readable to everybody. There's quite a few reasons to do something like that. Initially, this was to do an experiment, which I'll talk about soon. That was the first purpose, really to do an experiment. So this was like the content of an experiment. Meanwhile, I've been talking, for example, or invited to talk at the US Capitol. The reason being that people now see this book as a vehicle for workforce development for quantum technology. Because you don't need to be a mathematician, you don't need to have a physics or maths degree from the university to basically read this and understand fundamental quantum concepts. personally, I see this also as a vehicle for inclusivity of quantum, to the extent that, well, I mean, one part is you don't really need to know, have this mathematical background. There's of course places in the world where the education isn't the same kind of education in Western countries or stuff like that. And my feeling is even that with this particular book, for reasons I'll say later, non-Western countries can actually have an advantage. Non-Western cultures can actually have an advantage in understanding quantum mechanics, because I think this in itself, philosophically, is quite a departure from maybe even 2,400 years of Western scientific tradition. I'll try to elaborate on that later, because it's quite kind of important. But okay, so let's move on. So like I said, we wrote initially this book to do an experiment, and this is the Guardian reporting on that experiment. And so the claim here is that it's easier to convince the kids than adults of quantum mechanics. And this is not just a claim, this is something we proved in the following way. So, okay, our experiment. So basically, we wrote this book, and this book was to be a textbook of something. So we wrote this book, it's a text. We thought of it as a textbook for something. Then we took lectures, we generated lectures around this book. Like the entire book is put on in lectures. Actually, the lectures are now on YouTube, but they're not listed, so you can't find them if you don't know where they are. And the reason is we probably in the next week will bring out a web page with lots of resources around this entire program, which people can use for things I'll elaborate on later. But so we got this entire book filled in terms of lectures. Then we made exercises around it. So exercise sheets, exercise solutions, and all of that. And why we did all of this work is because somewhere in early 2023, we sent out these flyers to a bunch of schools in the UK, and we said, okay, if we're going to offer you a free course. We're going to offer a free course to everybody who wants it. And this is given by people from Oxford University, Quantinuum, and also we had some contribution from IBM. And the whole point is that you can learn about the quantum world in pictures. So we sent this to high schools in the UK. We had to restrict between, well, 16, also sometimes a little bit 15 to 18. And there are legal reasons for that, because otherwise it becomes really, really complicated to get permissions and things like that. But so we said, okay, who wants a free course over the summer? And if you take the course, it will take about 8 weeks. Then you will get a certificate, no matter how much effort you make. Everybody gets a certificate. That was the idea. Okay, by the way, here you see the dodo from the cover of the dodo book. And the book was written by myself and Aleks Kissinger, who pretty much took over the group at Oxford, which I used to have. I mean, so we got about 1,000 applications from the UK. And we selected about 60, 70 people for the course. I can't remember the exact number, something like that, just to make it practically feasible. So what was the course? Well, the course took about 8 weeks. So every week, the students were asked to watch one of the lectures. Then there was like an hour interaction with a tutor. They were giving some exercises every week, which they had to try to solve on their own. And then in the tutorial sessions, we then basically dealt with the exercise of the previous week. So actually what we were doing is we were basically subjecting these students, these high school students, to an Oxford University course. Because the structure of an Oxford University postgraduate, I should say a postgraduate course, is typically this. 8 weeks, that's a term at Oxford. Then you get your lecture, and then you get like a session with a tutor in groups of 10 people or something like that. That's typically our course is scheduled. So we ran this for 8 weeks. Like I repeat, everybody was going through, we got a certificate. But then at the end, we asked them, we said, okay, we got some questions here and we would like you to try to solve them. Just so we get some feedback on how well our teaching performance was. But what I didn't know is that all the questions were taken from Oxford University postgraduate exams. Of course, translated to the language of pictures. So questions were translated to the language they knew. And of course, we had in the questions, we had to avoid questions where there were concepts which went beyond what they ever heard about. So we had to be a little bit selective with the questions. We couldn't ask them about notions which you would only, well, when the statement of the problem would be something you only learn at university level. Of course, we avoided that. But anyway, we gave them this postgraduate. Well, let me look at time. Yeah, we gave them this postgraduate exam. The circumstances of the course were not at all ideal. It was all online. So the lectures were not live; they were recorded, as I explained. And something very unfortunate was that most of the students, they just put on black screens. We couldn't even see faces like in the tutorial sessions. And when they asked the question, they typed the questions. They didn't sort of spoke them. And I mean, from what I hear, there's two aspects to that. It's basically a consequence of this particular generation who grows up with mobile phones, but it's also a consequence of the fact that they all sort of were in lockdown during post-COVID, which also, from what I heard from psychologists, creates this sort of shyness. But anyway, so the circumstances were pretty bad, but in the end, 50% of the kids got a distinction. The majority passed, and 50%, almost 50% got a distinction on this exam, which is better than your typical Oxford University postgraduate students' marks. So in a way, they did better. This was very interesting, and then came as a big surprise to us. We were kind of hoping that a couple of them would pass. That was our hope, but like the result was like sort of mind blowing. So I mean, here are some statistics. So left top, what was the prior knowledge of quantum? Was basically so like 6-7%. They knew quite a bit, and then 14% knew at moderate knowledge, but the majority pretty much knew nothing. So the amount of time they spent is interesting. That's top, but because this was the summer. This was during the summer. Of course, sometimes they went 2 weeks on holiday with their parents. They may have had other. It also partly overlapped with what in the UK is called A-level exams. So it wasn't ideal. But if you look at the amount of time they spent per week, so the majority was between 1 and 4 hours. And this includes like watching the lecture and trying to do the exercises. So it was quite limited, the effort they did. The right bottom, you see, I mean, our selection of students was random. We tried to do this at random possible. We got 1,000 applications, and we tried to randomize over whatever information we got with regarding their performances at school, the kind of studies they did, the schools they came from, all kind of variables. We tried to optimize for randomness of the selection, and there was really very little difference between whatever schools they came from, whether they came from a state school or from a private school or boarding school. The average was around 60 for all of them. So very little difference. And social economical factors we consider too. The table top right is 2 questions, like the course strengthened my motivation and confidence. Like the majority said yes. Vast majority said yes. The course motivated me to pursue a STEM career. Again, the vast majority said yes. And then one thing which is not on the slide, but we had some sort of open question, like what can you say something what you felt most about this course? And the majority of the answers was it was fun. No, it was interesting. It was fun, and that's very important, because that's how you get somebody to get motivated to work hard if it's fun. So that's really nice. Okay. So yeah, I mean, we had earlier this week I had an interview with Physics World, and also one of the students who turned 18 meanwhile was present. So it's very interesting to listen to the student when this will come out with Physics World about what they had to say about their experience. So since then we've been doing quite a lot of effort around. I mean, this slide is outdated, to be honest. Quite a lot of effort around the world. So in Greece, so as you can see on the right, there's a translated version of the book, and they're now already teaching quantum at high school level, as approved, of course, by the government, using to a great extent this particular new language, which I'll explain a bit later. In Colorado, they're also moving very fast. In the same way, we have been talking to people from Stellenbosch over the past couple of months to also move forward here. And we ran a full course in Ghana. We ran a full course in Ghana too. And then there's some more stuff going on. Yes, around the world, much more than I'm actually showing here, because this thing is going very quick. We actually talked, this experiment was quite recent. It was publicized about a year ago. So our papers are not even out, to be honest. Our papers aren't even out. Right. So, I mean, I should tell you that to establish something like this, with all the outreach and also the complexity of setting such an experiment, there was lots of people involved, of course, many people. That's it's not something easy to set up, and the time, the preparation it took, and because there's like ethical and legal things you have to deal with, it's not easy. It's quite complex, the whole thing. Okay, let me now start with what this was all about. So basically, the language we use is very simple, and already indicated this with Penrose. It's a language of wire and boxes. So you got wires, and of your wires you think of as your systems or something where physical particles flow. And in the boxes, they may have inputs and outputs of these wires, and then the boxes do something to whatever goes through the wires. They alter it. And then the key concept is the fact that you can compose these. That's all. So these are your sort of mathematical primitives and your mathematical operation, your elements, if you want to say, but obviously these are objects and morphisms in category. And then your main operation is to plug them together, which is what in category theory land is the symmetric monoidal structure of these diagrams. And why? I mean, initially I said that Schrödinger wanted to be composition of systems like your first-class citizen, and you can see this here. Here you see two wires side by side, and this means we're composing systems. This is like the equivalent to using a tensor product in your usual quantum mechanical formalism, the fact that you put two wires side by side. So the horizontal direction is like composition of system. The vertical direction is like composition of processes. It's where you do one thing and then another thing. So the way you read this diagram, of course, is things come in here and these boxes act on them and then they spit out some stuff. So that's the basic. Of course, this is super general because you can fill them with whatever you want. You can fill them with electricity wires and sort of electricity boxes, or with like water, of course, not at the same time. And that's what the types in category take care of, that you're not going to connect your electricity to your water to your electricity, of course. That's the point of the objects of the types in category theory. Or, I mean, this can be a computational network or anything like that. So you can fill them with anything you want. So they aren't particularly quantum per se. So what do you do? What do you want to fill them if you want to make them quantum? Well, you fill them with spiders, something we call spiders. So what is a spider? Well, let's first try to understand what is a wire. So a wire is a thing with two endpoints. That's a wire. A wire is a thing that connects two endpoints. And what can you do with wires? You can plug two wires together. Base plugged it together, you get again a wire. In electricity terms, you can think of this as an extension lead, and you can just plug two extension leads together. Now, these wires, we consider them as elastic. So if you connect two elastical extension leads together, it's kind of a waste of extension lead because you end up with the same as you started with. So it's not very interesting. So this is a spider. Now, what is a spider? A spider is a little bit like a wire, but instead of two endpoints, you can have multiple endpoints. Or maybe one or none. I mean, it's all, a spider can be anything. It doesn't matter how many endpoints you have. But the behavior of a spider is very similar to that of a wire. If you glue two spiders together, you get again a spider. Of course, now you have to do a little bit of countancy on the number of legs. You have to count how many legs come in and how many legs come out on the left-hand side, and it has to be on the right side the same. So these things fuse together. So that's a very simple rule to remember. That's a rule about spiders. So basically, you got your ingredients of your language, which are the spiders, and then you got some rules, and the rules are basically the spiders fuse together. Well, they fuse together if they happen to be of the same color, or of the same, whatever you want to call that, the same label or whatever, if they're the same type. In quantum mechanical terms, it actually corresponds if they are the same observable. So to go a little bit to mathematics, so basically the usual way mathematicians would call these spiders, it's called Frobenius algebras. It's not ordinary Frobenius algebras, it's a Frobenius algebras which are supposed to be special, and special here is a technical term, by the way, special, dagger, and commutative. So, I mean, I don't, in the idea of the spider as I presented as a wire, this is all implicit. All of that stuff is implicit. You don't have to state it. The whole point is basically to reduce this definition of dagger special commutative Frobenius algebra to a little representation which intuitively captures all of the algebraic equations you would want to. So if you go to our papers before, this will all be like in terms of dagger special commutative Frobenius algebras. I've got a number of papers with Duško Pavlović about that, which some people here will know, and Jamie Vickery. So in the sort of algebraic formulation of all these things. But of course, in the Quantum in Pictures book, we want to make this in a way that people don't need to know this algebra or algebra at all. So, okay, and then you can actually prove that this law, together with the ones which I said are implicit, the commutativity and all these things, there is a theorem you can show that this law of the fusion, if you want to interpret this in the world of Hilbert spaces and linear maps, well, let's say the category of Hilbert space and linear webs with tensor product and the dagger to be like the adjoint, the linear algebraic adjoint, then this equation forces a family of spiders to correspond to an orthonormal basis. So this is an what you see here is an alternative definition of an orthonormal basis. Doesn't look anything like it. And what makes it special, it's a definition of an orthonormal basis without making any reference to typical linear algebraic structures such as sums, such as scalar multiplication, and the typical things you find in the definition of a vector space and linear algebra. You don't need all this additive structure here. It's just like formulation of an orthonormal basis in terms of tensor product language and tensor product language only. So that's a key thing. So that's sort of what's happening here in the mathematics in the back, in the symbolic mathematics in the background. Okay, let's go to Spiderland. So we got spiders. There's a rule on how they compose for spiders of a particular color. Okay, now suppose we've got spiders of two colors, two different kinds of spiders. Then the rules are different. So we will always consider only two kinds of spiders from now on. So you get like these green spiders and these red spiders. And if they meet, if they get composed and there happen to be two wires connecting them, then these two wires vanish. I mean, you see a somewhat violent interpretation here, like it's as if they don't like each other. They each give each other like a little bit of an uppercut, and then these arms fall off because they are weakly connected, these arms. So we got two rules here. Oh, sorry. Spiders of the same colors fuse. It actually doesn't matter how many wires are in between. Spiders of a different color, whenever there's two wires in between, then these wires vanish. So that's two very simple rules. May look very silly, but I'm now going to start computing with this. So for the physicists in the audience, in the same way as I said that this characterization of this fusion corresponds to basically such a family of spiders corresponding to an orthonormal basis. This law basically says something about how the green bases and the red bases relate to each other. And basically what they're saying is the green base and the red bases are what is called unbiased. I mean, this is a term physicists use. More traditionally, they used to call these things complementary in the more traditional literature, complementary. And the way you have to think about it is if you think about each of these orthonormal bases, like you take these bases that a vector of one basis will be equidistant to each vector of the other bases. So the inner product between any vector of one basis will be the same for each vector of the other basis. Like I'm trying to, so basically this would be, for example, you got a basis like a two-dimensional basis, and then the other basis will be the sum of the basis vector and the difference of the basis vectors. so that they always at the same distance if you take the modulus of the inner product. So I'm talking about the modulus of the inner product or the square inner product or like that particular measure. So they call that's where the word unbiased comes from. If you think of them in terms of physics, in terms of observables, it means that a measurement of one observable won't be biased to any outcome if you take as the initial state an eigenstate of the other basis. Yeah. So that's what this equation actually physically or in terms of vector space is expressing. So again, I repeat, same fuse, different like if two wires they go. So okay, so we're going to look now at something which is a quantum program. A quantum program is basically you got a bunch of quantum systems, typically called qubits, two-dimensional, and then you do stuff to them. You apply gates to them, quantum gates. I'm going to take a very simple program here. So you got 3 qubits. The qubits correspond to these yellow wires. And you got also 3 gates you apply to them. They correspond to like basically this composite of 2 spiders. So you have to, so basically we plug a red and a green spider together and we treat them as a gate. Now you can say, what does it mean to have an horizontal line? Well, it turns out that if you first take the green spider and then 2 wires coming out and 1 spider of the green spider goes into the red spider, or do it the other way around, it's the same thing. It's the same thing. That's why we can write this wire horizontally. And that makes calculus very easy because it doesn't really matter whether the wires are really inputs or outputs. The spider rotation is completely neutral to that. But you can put it as an input, you can put it as an output. As long as the connections are the same, it doesn't matter. It really doesn't matter. So okay, so we got 3 systems, three operations. And for people who know about quantum operations, it turns out if you take the green spider to correspond with the 0-1 basis, like the Z basis, the so-called Z basis, and the red spider corresponds with the so-called X basis, the plus-minus basis, then this is a C0 gate. Then this will be a C0 gate. And the green is the control, and the red is what you control. Now, so we got a circuit here with 3 C0 gates, and we want to know if we can simplify this. Now, we're going to forget about the fact that these are C0 gates, and we just think in terms of spiders. Okay, we see 3 dots, 3 green dots connected, and 2 red dots connected. Yeah, 3 green dots connected, 2 red dots connected. They fuse. Now, we see 2 wires between a red and a green. They go. Now we see a red dot with two wires, a spider with two wires. Well, that's just a wire. Because 2 endpoints. So we basically simplified this circuit to this circuit using these 2 laws of spiders which we just have. Of course, this is completely trivial example. This is a completely trivial example. But as a matter of fact, this way of simplifying quantum circuits, using these spiders, using these Frobenius algebras, using things which go back into category theory, for those people with a category theory background like Carboni and Walters and Kelly and a lot of Australian category theory, because that's really what I'm showing here. There's a lot of Australian type category theory going on behind the scene. Well, this simple rules is now the state of the art on how to simplify quantum circuits. This is used by IBM, this is used by Google, this of course is used by ourselves. This is used by all the major companies now, this sort of mathematics. I think there was a typo in my abstract that I said is not, I think that I wrote it's not widespread in quantum industry. Actually, I want to say it's now widespread in quantum theory because it is widespread. Everybody's using this type of techniques now in really very practical applications on quantum computers and trying to get something on a quantum computer. Because basically what we're doing is we're optimizing a circuit. We're making a circuit as simple as possible so that even if your computer can't take like big circuits, you can still do it because you simplify it enough. And I'll give some other examples later of where this is used now in practical quantum computing, pretty much all over the industry. Okay, so we just gave an example of a calculation with these spiders, simplify a quantum circuit. Now, one of the coolest thing I think about this spider notation is how simple it makes the difference between quantum and classical. Quantum and classical in terms of, okay, you may have classical bit, like which can take values 0s or 1, or you may have a quantum bit which is described in a two-dimensional Hilbert space, which if you like only care about the norm, which you should do in quantum mechanics, then basically they live on a sphere. So your states live on a sphere, and we now want to distinguish them in diagrammatic terms, like the classical and the quantum. So the rules are very simple. Like classical, so far I used like single wires, but from now on, when you see a single wire, you're going to think of it as classical. I'm saying ordinary because classical is such a weird word if you think about it. If you're not a quantum mechanical person. Classical one thinks about like sort of far in the past, but the classical perception and world is still around us. So why would you call it classical? So let's say ordinary. And then the two wires together we call quantum, because that's how we're going to represent quantum. For those people who actually know quantum mechanics and quantum mechanical formalism, this is kind of already baked in usual formalism. When you write down a density matrix, which is a representation of a mixed state, which is a state where you've got a lack of knowledge about what the actual state is, then basically what you do is you take your vector and then you double it. And that's so typically this means if you got a cat, you adjoin a bra, and then the two together you can sum, and this is probabilistic mixing, and that's how you build a density matrix. And that's kind of corresponding to this doubling here of the representation of quantum as double. That's the way you should think about it. And just to give some, so basically what you see here is the passage from quantum to classical. And what really happens formally is if you would stick a density matrix at the bottom, what comes out at the top is just diagonal. Diagonal, which is a list of numbers and makes up a probability distribution. So in principle, these wires, they carry implicitly, if you want, density matrices and probability distributions. You don't have to know what they are. You can still like read your picture, reason with your pictures. But if you know what a density matrix is and a probability distributions, you have to think that what flows in the double wires are density matrices. What flows in the single wires are probability distributions. And so effectively, what we see here is a quantum measurement. This is a quantum measurement. You have some quantum input and you get some classical output. So this effectively is the representation of a quantum measurement in this diagrammatic language. So it looks very simple. I mean, for people who have taken a course of quantum mechanics, then you need to take a self-adjoint operator. Then via the spectral theorem, you diagonalize it. And then after diagonalization, you got a spectrum of projectors. And then this projector corresponds to the measurement outcomes. And then there is a protocol on how you compute your probabilities. All of what I'm saying here is implicit in this notation already. It does exactly that if you interpret the spiders in the world of now in the category of density matrices and completely positive maps and all of that, which is pretty heavy to deal with. If you interpret it in that land, then this does exactly the same what I was describing, what you find in any textbook on quantum mechanics on how you deal with a quantum observation, quantum measurement. So this is the opposite. You've got a classical system coming in, which can be a bit, a 0 and a 1, and then you've got a quantum system coming out. So this is basically turning a 0 in quantum state 0 and a 1 in quantum state 1, if you want. That's how you think about this. So we got these two ingredients, going from quantum to classical and going from classical to quantum. And now we're going to start doing computations with them. Okay, here is the first simple thing you can do. You basically take a classical system, you encode it in your laboratory as a quantum system, and then you measure it. And the encoding and the measurement is along the same observable, along the same orthonormal basis, if you want. So if you do this, you do something pretty useless because what comes out is exactly the same as what comes in. So it's the same as doing nothing. Huh? So that's very easy. Now, if you encode in one basis and you measure in the unbiased or complementary basis, well, then the story is not at all the same. What you see here now is there's two wires in the middle. There's two wires in the middle between red and green. So they're going to vanish. They're going to vanish. And now you see that the input at the green dot and the output or the red dot are completely non-connected. From what you can immediately deduce that whatever comes in at the green dot bears no connection to whatever goes out at the red dot because there's no wire connecting them. And essentially what this means is that the outcome is going to be random, independent of what the input is. So like this red dot with a single wire is actually randomness. You don't have to know about randomness to draw the pictures, but that's how you would want to interpret it. Now let's go to a much more interesting example. So what you see here is you got a green dot with a double wire coming in and double wire coming out and a single wire coming out. So what is this? This is so again, this is a quantum measurement, but it's a different kind of quantum measurement. It's a quantum measurement, but the quantum system comes in, but it's still alive after the measurement, and it comes out too. So it comes in, it comes out, but you also get some classical information, some information about what has happened. So this is what people call a non-demolition measurement, a measurement in which you don't destroy the system. These things can be done, they've been done for a long time. And so what you see here is a concatenation of 3 measurements. You measurement in green, measure in green, you get some outcome. Measure in red, you get some outcome. Measure in green again, you get some outcome. Looking at the pictures, we see twice a double wire between red and green. Okay, so they go. So what this is telling us now is you got these 3 classical wires or ordinary wires coming out, but the one from the first green dot and the one from the second green dot are in no way connected. They're in no way connected, which means they will be completely independent. Okay, so this is kind of awkward if we think in a sort of classical ordinary terms. So you got a thing, say car. You look at it and you ask, okay, what's your brand? Well, let's not take a car. Well, let's take a car. What brand are you? And then you ask, what color are you? And then you ask again, what brand are you? And it turns out that the first answer you get to the brand and the second answer you get to the brand is completely unrelated. They have no relationship to each other because they're disconnected. And of course, the quantum mechanical explanation there is that you do another observation in the middle, which basically is unrelated to the first and the last one, and this completely disturbs the connection between those two. So it disturbs the system in such a way that what comes out of the red one has nothing to do anymore with what came out of the first green one. And so those 2 green observations are completely unrelated. So there's probably 1,000 books written about this phenomenon, and it's not so easy to calculate in Hilbert space exactly what is. I mean, but you can just get this from these simple pictures and these simple rules we've been observing. So it's quite easy. Anyways, so these are a few simple rules, and you can prove a lot of stuff just with these 2 rules, like things like quantum teleportation and many like interesting phenomena, quantum mechanics. You don't need anything more. Now this is not whole of quantum mechanics, unfortunately, yet. So I'm going to add a little bit of structure to my formalism. First of all, I want to decorate my spiders with phases, because of course angles play an important role in quantum mechanics, and so we bring them in behind. Initially, we wanted to do this with phases of the moon to even make no connection whatsoever to symbols, but after drawing a lot of these pictures with phases of the moon, we gave up because it was really hard to draw. So we did commit to actually using angles, and then basically the idea is that you can decorate the spiders with angles, and they just add up. They just add up. That's it. They just add up. So that's a very simple rule. They still fuse, but they add up. And then there is another rule, so basically the previous rule we have, and now I'm going to talk a little bit graph theory alike. You see, if you got, so you have to think of the picture of the left-hand side like as a 2 cycle in a graph. You got a 2 cycle in a graph, and then the graph vanishes, and then the 2 cycle vanishes because simply the edges vanish. Huh? Now, what do you do if you've got a 4 cycle in a graph and you want to simplify it? Well, then you apply this rule. So you see on the left, we've got a square. On the right, we don't have a square anymore. A lot of mathematicians may recognize this with a little bit of twisting as like the law which supports a quantum algebra, like a bialgebra. So this is basically one of the rules of a bialgebra that you see here, twisted and a little bit, but that's essentially what it is. Now, essentially this rule And the rules I've given you now, like you add these phases, you got fusion, you give this algebra structure, they essentially take you to the following situation, which I've sort of cryptically depicted as follows, that using all these diagrammatic rules, which you find in this book, Quantum in Pictures, you basically can derive any equations you can derive also in the Hilbert space formalism. So it's basically, this is what we call completeness, or in logic, it's called completeness, that you got enough rules to basically replicate all the equations you can derive in a model. And this is true now with these diagrams with respect to Hilbert space. This was proven by a number of my PhD students in 2017, 2018. Highly non-trivial to prove this, obviously, highly non-trivial. It was never even conjectured that it would be true, because we didn't even believe this ourselves, but in the end, it sort of ended up being that. And now, I mean, this language is just used widespread in all of quantum computing. It's used widespread all over quantum computing, doing things like error correction and very, very crucial engineering-like tasks to, yeah, basically make quantum computing and everything related like move very fast, because it's moving very fast at the moment, I should say that. I mean, I could have given a talk specifically about quantum hardware, but I mean, I chose to talk about this more, both educational and technological, new kind of formalism, which, as I mentioned before, really came out of category theory historically, and then a particular branch of category theory. So very soon, I mean, very soon all these resources will be released online. I mean, I don't think I've got much time left. So let me just, so that's, I think I pretty much want to end here. I just want to very briefly mention something I won't have time for, but at the moment, this kind of language and formalism, in most of my time at my day job, we're using to make a scalable and interpretable form of AI, which means AI that we actually can understand, that's not just constituent of black boxes. So we do this on quantum computers. We're doing AI on quantum computers, and it intrinsically becomes interpretable and scalable. Of course, there's no way that we can compete at the moment with what the large language models are doing, but we got a lot of very promising properties. And for example, this work specifically, which you can read about, I'll point at a blog post, was selected of one of the 10 best research stories in all of quantum computing. So it was basically doing AI using these pictures and getting a lot of nice features because of using this diagrammatic structure. If you want to read about this, there is a blog post which you can Google. It's called Talking Quantum Circuits, and we talk about this particular thing, and then you get also the scientific references for all this work. Since I promised it, let me scroll a bit forward. I'm just going to skip all of this because I don't have time. Just want, for category theoreticians, just want to say you, of course, recognize Jim Lambeck, who had a role in this development. And we do have a software which you can download called Lambeck. Oh, no, it's not here. Called Lambeck, yeah. So there is a software package, Lambeck, which does all this natural language, quantum natural language processing for you. So which you can find online if you Google it. And we also have used the same diagrams to make music. And I've always wanted to be a musician in my career. And the first song ever generated by a quantum computer was by us. We called ourselves Ludovico Quanthoven, and we ended up #1 in the classical charts. And if you like music festivals of the heavier kind, then last summer and also next summer, you can find me playing on stages using effectively quantum instruments as part of the show. I'll stop here.
Yeah, thank you very much for an excellent talk. That was, I think, perfect for the 14th of March. Yeah. So I'm sure there are questions from the audience physically in the room and from the online audience. Let's start with the people that are here. Any questions? Yeah, Zurab and then Bruce.
Could you maybe say a little bit more about quantum instruments? So is this something that builds on these diagrams that you showed us?
So Yes and no. Yes and no. Yes and no. So, so some of them are quite basic. You basically have some controller, which in my case is a guitar, which can be some sort of movement detector or something, or just a keyboard. Then whatever information you get in there, you send to a quantum computer, and then you do something where you really use the qubit or whatever lives inside as an instrument, as a physical instrument. It's a little bit like a synthesizer if you want, but instead of like just a classical oscillator, you basically have a qubit which you can rotate, which you can measure, and things like that. And that's basically your instrument. So it's a different kind of instrument basically that you do. Then on the other hand, in what we did here, like I'll just go a slide back. So that's one of the things, and there is a company called Mod Quantum which is producing these sort of things. So what we used here was quite different. I mean, I'll show it here. This is Brian Eno, in case you know him, one of the most famous producers in the world. So we basically used the work we did in DiscoCat quantum natural language processing and all that, which is a theory about meaning in language. So you use diagrammatic structure to compose meanings in language to turn meanings of parts in meanings of the wholes. So it's a theory which contains structure, as in grammatical or linguistic structure, and meaning, as in what is the meaning of a word. So we took out the meaning of the word and we put in musical meaning. We replaced linguistic meaning by musical meaning. We replaced linguistic grammar by musical grammar using the same diagrams. And so basically we had like, instead of a language of linguistic meaning, we had a language of musical meaning, compositional language for musical meaning. And that's what we used to then generate some music. So the program is called Quanthoven, so which you can find online. Program is, we have an article about it, a scientific article. It's, if you Google Quanthoven, because nobody else ever called anything Quanthoven in the world, then you end up with that article. It's on the archive, and it's also in this book, which Brian Eno, as you see, is reading here. The two people around him are two of my collaborators on this work. So it's a mix of the two. So for some things we actually built further on this, and then there are some other things which have been produced, which are just say plain quantum hardware based things. And we are now in the process of building things which combine the two. Again, this is all very new. The company was created. I mean, I'm one of the founding shareholders. That was like a little bit over a year ago. It's almost no more than a year old. So, but yeah, I mean, like I say, we're using these things at festivals, and more artists are starting to use this because it's just a new instrument. And when you get a new instrument in your hands, you do different things. That's kind of how it works.
Thank you very much.
Was another question here, Bruce? The microphone is coming across.
Hi, Bob. Yeah.
Hey,
good to
Bruce.
see- Okay. Yeah. Tell us a bit more about the interpretable AI with the quantum pictures. Yeah.
Yeah. So I mean, so we've been doing this kind of for a while, and I think you're actually aware of the stuff like Marnouche and myself and Steve Clark were doing years ago. Where, I mean, here is a number of, I'm just scrolling back. Where did I put this pen? Yeah, here. So there is work which goes back to 2008, 2007, 2008 in Oxford. I think you were around that time in Oxford. And there was like an open question, like we know how to deal with meanings of words, and that's what people, of course, are doing now. Everywhere in machine learning, you represent words by vectors. And at that time, this was a purely academic activity, by the way, and people represented these words by vectors, and then you could see whether two vectors were close to each other by computing the inner product, and that meant then that these words were similar in meaning. But there was no sort of mathematical account on how you compose words like we compose words in sentences in order to produce meaning of entire sentences. And so we then basically took together compositional structure in language, going back to people like Lambek and Chomsky, and together with vector meaning. And I mean, it was quite nice. It was quite simple. I knew from Lambek that, well, linguistic structure was a compact closed category, just like cups and caps. That's pre-group semantics. And then on the other hand, vector spaces, they naturally also form a compact closed category. Because the cups and the caps come with tensor product structure. So it was very naturally then to just map one on the other, to map the grammar on the category of the vector spaces. And this then mediates how their words interact to form meanings. That was kind of the first thing we did there. And I mean, nobody else had come up with a theory where you compose like vector meanings or anything like that in order to come up with like meanings of wholes. And not too long after so basically what you got there is like you got a diagram, a tensor network if you want, and you know what the ingredients mean, you know what they mean. So basically like we then showed that you actually get quantum advantage, algorithmic quantum advantage, if you would execute this thing on a quantum computer. This was a theorem from 2016, and 2020, we effectively did this on quantum hardware. We did a task which was question answering using this formalism quantum hardware. And this would have been impossible in any other way that people now do machine learning, because these quantum computers were really small. And the fact that we actually had structure at hand, like this compositional structure, made it possible with very little data to actually do useful things. And like I said, this is all implemented in this software Lambec. Now, more recently, we work with a new, more advanced, more sophisticated theory of language, which I started in this paper, The Mathematics of Text Structure. And the idea is now that language, that texts, we're not talking about sentences anymore, that texts correspond to entire circuits. So big texts correspond to entire circuits. And so you can think of it as a neural net if you want this data. But of course, you know everything which is going on inside. You completely understand the structure of the circuit. And that's the sort of thing which we have now been doing on quantum computers. And again, we find incredible, I mean, I don't have time to, so you can read about this in this paper, for example. I know you know all the background to this story. So, and some amazing properties which we found is that if you represent these texts as circuits, that all languages become the same. It doesn't matter which language you take, the circuits become the same, which is not the case, for example, for a categorical grammar a la Lambec or Chomsky, or generative grammar a la Chomsky. So it's a much more universal representation, these circuits, and it naturally lends itself to be stuck on a quantum computer again, because it's a circuit, which is exactly the sort of thing a quantum computer likes. So we have some theorems now where we expect that if you want to run a text as a circuit in this way, then on a quantum computer, you would get exponential advantage in your execution for basic tasks like, and then basically asking something about a text. You run the text, detective novel, you ask like, who's the murderer? Well, to do this task on a quantum computer, you would get exponential advantage now with this representation of things. And we basically did this, like we did this about 8-9 months ago on our own quantum computers. We got incredibly nice result, incredibly high fidelity. And one of the nicest things we saw is that thanks to the structure, again, thanks to the compositional structure, you can train very small, even classic, something that you can easily do on your laptop, and then test very hard, something that you can't do anymore on any existing classical computer. And we showed that is actually, that this is doable, that you get these nice properties. And the sort of interpretability that you've got here, interpretability is a word that people use informally. So we wrote a paper about it, I think. I don't know if I have a slide about it. Yeah, we recently, I mean, I wrote this paper specifically about compositionality, the kind of compositionality you need to understand these things. And we have this paper specifically about interpretability in AI, which defines what it means to interpret a compositional model, or for it to be interpretable. It's not just that it's compositional, because of course neural nets are compositional. It's something more, which wasn't really formulated at any point. So yeah, you can read about this. I mean, I think I showed the reference in this blog post. Everything I'm saying now, you can find here. You just Google it. And yeah, that's a story. It's very much an ongoing story, but that's mainly what my team is doing now in Quantinuum. My team based in Oxford doing in Quantinuum, this kind of stuff.
Thanks. That's very cool. Thanks.
Thank you. Are there further questions here? Yeah, at the back, please.
I have a question related to whether your diagrams would extend to quantum field theory. In quantum field theory, there is, for example, in scattering, the representation of Feynman diagrams. So would spiders and this formalism extend similarly to quantum field theory?
Okay, there's a lot of things that can be said about it, and actually one of the persons who can give one of the answers there is Bruce, who was just asking the question. So let me first make one distinction. Like Feynman diagrams, they are like a calculational tool. They help you calculate. And you do your diagram, and then you do your calculation, and you follow the diagram to do your calculation. What I was talking about here in the beginning is actually a substitute for a Hilbert space. You do everything in terms of diagrams. You compute your numbers and your probabilities, everything in terms of the diagrams. So that's one crucial difference between the two. Now, people have done sort of more abstract field theory, which they call topological quantum field theory. And also the spiders come in, and I know Bruce has papers where they use these Frobenius algebras as part of the characterization of your possible topological quantum field theories. But those are theories where you basically only care about the topology of your field theory. Now, there is work by some of my former students and by some other people. I think one name I would coin here is Stefano Goggioso, my co-author of the Quantum in Pictures book. He does a lot of work on a quantum field theory within this formalism. So everything I've been presenting today in the beginning is really just about two-dimensional systems, two-dimensional quantum systems, qubit. So that has been generated to finite dimensions, and people are now also working infinite dimensional things. It's a bit tricky, and people have been using different approaches. Some have used like a standard non-standard mathematics formulation of Hilbert space to basically make things like cups and caps survive through the passage to the infinite dimensional continuum of quantum fields. There are some other ways to approach it. There's quite a lot of work being done there. And I know, for example, there's a paper soon going to come out where there is even a quantum gravity calculation using this sort of diagrams. So so I would say pretty much anything finite dimensional is done. It's done. When you go to field theory, there's a lot of work being done towards that end goal at the moment. I mean, if they can make that end goal. So we for a while we've been having a large joint grant with Carlo Rovelli, specifically on one part specifically of taking these diagrams and bringing them all the way to possible theories of quantum gravity, like, for example, his favorite loop quantum gravity.
Oh, thank you very much. Are there questions from our online participants? Not for the moment. Then, Bob, then thank you so much. We will just now... sorry, there's one last question from Zurab.
Sorry, one last question indeed. Yeah, thank you very much for the talk and the answers to the questions. So you said that your company is relatively new. Does your company have sort of internship opportunities if, for instance, we want to send some of our students here to do some kind of internship?
So are you talking about the music company or Quantinuum?
Oh, I'm sorry. I'm talking about the Quantinuum. I didn't realize.
No, I mean, when I was talking about a year old, it was the music one. So
I see.
Quantinuum is like, I mean, this started as Cambridge Quantum, and then there was a merger with part of Honeywell, and that made Quantinuum. I mean, it's a large thing now. It's like between 500 and 600 people. So it's quite a substantial thing with offices. Like I mean, there's definitely internship possibilities. Definitely, we have an internship program rolling, and of course there's different. That some people come with external funding, some people need funding. So there's different formats, but there's definitely internship possibilities. And so you got the company as a whole. I've got like a team also in Oxford, and then the team in Cambridge is led by Ross Duncan, who's the co-inventor of the X calculus. So that's also a good place to actually go for an internship. There's also people working a lot with tensor networks. There's a group in Munich So there's quite a lot of possibilities for. There's also a group in London, but yeah, so there's quite a lot of different options for internships. Just to our hardware is being made in Colorado now, in close to Denver, and we also have an office in Tokyo where there's also actually a few category theoreticians too there. So there's quite a few different options for internships. Yes, sure.
I wonder. Thank you.
Bob, before maybe we send you something and someone as an intern, we should make a plan to have you in Stellenbosch, because now we will, outside this venue, we will have a drink in your honor to thank you and to celebrate the International Day of Mathematics. But unfortunately, we don't have yet a teleportation system to send. We will make a plan to have you in Stellenbosch as soon as possible.
Thank you so much.
And offer you something. Excellent. So thank you very much, Bob, for your time. And thank you to all the people present here and online. And we will have another colloquium on Monday. Yeah. See you here again in the same place. Thank you very much again, Bob. Thank you.
Thank you all. Bye.